just so that I don't forget to do it later. Alrighty. Alright, so I can see the YouTube stream is up and running, so that's good. Alright, we got about 20 seconds left before I start the lecture. And what we'll do today is to go over the homework assignment. And I want to point out a few things, just a few observations. And then we'll talk about the new homework assignment. And then we'll see how much time we have left to talk about some additional topics. Alright, so it is time to start. Alright. Just looking at the number of people in Discord, about 10, and then the number of people on YouTube, which is currently 0. So I'm thinking the class size is now down to 10. I'm just kidding. I think the rest of the class is probably either late or planning to watch the recorded video, as long as they remember to watch the video, because sometimes people just forget. Alright, so this is still a synchronous class, and I think we should probably make the best use of a synchronous class, just by being able to ask questions during class. Alright, so first thing first, we're gonna look at the solution of this one, and let's go ahead and do it. So what I'll do is I'm going to draw the diagram, of this particular graph on the side. So we're going to do about the same thing. I would like you to open up the algorithm on the side. So this way you can refer to the algorithm as I talk about it, and then I'll use a spreadsheet, just like we use that spreadsheet in class to log the trace the algorithm. All right. So let me open a new page. So a few people, drew diagrams and sent it to me just to make sure that the diagrams are correct. That is fantastic. Okay, that's a good way to start with this homework assignment. So I'm gonna draw a small picture. So we got A, B, C, and vertex D. We got an edge going from A to B, like that. And the distance of that is 1. We got one from A to D directly, like that, and that edge has a distance of 11. And then from B to C, we have an edge that has a distance of 2. And then from B to D, we have an edge. Oh, okay, never mind. I just made a mistake. Okay, that's okay, because that edge is supposed to go from A to D directly. So A to D right here, and it has a distance of 11. And then let me just double check. BC is 2, and then from C to D is 1. There we go. Alright. So let me just count the number of edges. Oh, the BD edge also has a distance of 3. Okay, I think that's correct. Alright. So Emerald, your mic is on.
Oh, my bad.
Yeah, no problem. Just want to remind you. Alright, so this is the diagram. I know it doesn't look very good because the pixelation is really bad. The software doesn't somehow do the dithering correctly. So it's kind of it just doesn't look very good. However, the graph is done correctly. So now the question is, how do we trace this algorithm? So the next thing I'm going to do is to open up the algorithm itself. Okay, so I'm going to open it in a new tab and scroll to graph theory, and you should probably do the same. I'm hoping that you guys already know where to find the algorithm itself. So here's graph, and then we'll go ahead and open up the algorithm. And this one is Dijkstra's algorithm, so I'm just going to go straight to the algorithm itself. And for those of you who just want to go like, but where's the link of that? I don't want to go through all this navigation, so I'm putting the link in the text channel. And then I'm going to pull this tab off to the side of the screen, so this way I can focus on just the spreadsheet, on the recorded portion of the screen. And there we go. So go to Office, and I'm going to use Calc, which is a localized application. There we go. Alright, oh, actually, what I wanted to do, okay, I take that back. What I want to do is to, I'll do it exactly the way that you are supposed to do. So I'm going to download this Google Sheet first. So I'm going to download this Google Sheet and then open it in LibreOffice Calc. So here's download, and I can download it as OBS. Alright, need to change it to LibreOffice Calc. There we go. Alright, and here is the document that I just downloaded. So obviously the first thing we need to do is to fix this so that it does not, so that it reflects what we need to do. So we have to remove all of these rows because none of this is going to apply. So we're going to remove all of those rows, and even the columns need to be adjusted because there's no vertex E in our case. So we're going to have to remove this column. So just remove the entire column. There we go. And now it's going to resemble what we need to do. Alright, so let me put this on the side. Have the graph to show here. There we go. I can actually put it down lower like that so you guys can still see it. Right there. There we go. This gives me a little bit more space to show the spreadsheet like that, like so. And like that. Alright. Alright, so now we are going to follow the algorithm. And I can, no, this will work fine. Okay, so now we just need to follow the algorithm. The first two lines of the algorithm, the let statements, that's really just the parameters. And we have one single destination, which means S as a set only has one single element, which is vertex D in our case. So starting on the third line, the for each statement, we are initializing all the vertices that are destination vertices, and we only got one, which is D. So let me just unboldface this one. Now you don't have to do this, when you're working on this, but we want to initialize L of D to be 0, because L of something is the length of the shortest path known up to this point from that vertex to a destination. But since D is already a destination vertex, so the length of the shortest path from D to itself is going to be 0. All of the other vertices has infinity, because that's what the fourth statement from the top in Dijkstra's algorithm is instructing us to do. We initialize all of the other L values to infinity. And then on the fifth line, we want to copy S, which is the set of all the destination vertices, to Q. So that means Q is going to be a set with only one element in it, which is D. And then the sixth line from the top is in the initialization of E prime, which starts with an empty set. So row 2 is representing how we are initializing all of those variables that we need to use within this algorithm. Are there any questions about this step? Okay, no questions. All right, so now we are getting into the while loop. The while loop says as long as Q is non-empty, we still have to perform the iterations. So within the first iteration, there's really not a whole lot of vertex C to choose for our local variable V. So that can only be D. And then we're going to remove that element from Q. So that means Q is going to be an empty set. And then we are moving on to the for each inside the while loop. So the for each is really just looking at all the edges that are incoming to vertex D. There was one person who showed me a trace where that person was tracing the outgoing edges. That would not be correct. So we are tracking all the incoming edges to D. So from what vertices do we have a direct edge to get to vertex D? That is what we are evaluating. And so W is where we are coming from. So in this case, W is going to be A, B, and also C. So the question is, which one should we use first? It doesn't really matter. Okay, we can use vertex C first. So if I choose vertex C, this one does not have a column for T. So if you do not make your own column of T, that's fine. Okay, I'm not going to take any points off, but it might be handy to do that. So I'm going to insert it here to have an extra column for T. And in this case, T is, oh, never mind. I don't have a variable T in Dijkstra's algorithm, only in A star. So forget what I just said. It's okay. All right, so this is the most important part. Okay, I have no idea why this is an issue, but the important part is we have to evaluate the condition, which is L of V plus D of E is less than L of W. That is important because if that condition is true, and only if that condition is true, we continue with the then portion of the algorithm. Let me show you which part of the algorithm I'm referring to, just to make sure that we understand which part we are referring to. So I'm talking about this portion here. Okay, we have to evaluate this less than if it is true, and only if it is true we go through with the rest of these statements. If it is not true, then we do not. We skip over and then we just perform the next iteration of the for each if there's a next iteration for the for each. All right. So now we are going to look at this one. So we are looking at the L value of D, which is 0, and then we want to look at the distance from C to D. So the distance from C to D is just 1. 1 plus 0 is 1. The current L value of C is infinity, and we have to ask, is 1 less than infinity? The answer is true. So in that case, we got stuff to do because now we have to update a few things. According to the algorithm, the first thing we need to do is to update the L value of vertex C. So now it is just 1 because whatever we use on the left-hand side of the less than relation or the comparison operator is what we use to update L of the variable W, but the variable W has is specifying vertex C at this point, so we are updating L of C, so that becomes 1. The next thing we do is remove all the outgoing edges from C inside E prime, but there's nothing, so we keep E prime the way it is. And then we are going to add the edge of CD into E prime. So we add CD into E prime like that. And then we update Q so that Q also would have vertex C in it. So that's how we update set Q. So this row here, row 5, is reflecting all of the things that we need to do once we get into the then portion of the conditional statement. But before we get into that portion, we have to evaluate the condition. So it will become important, of why I said this portion is really kind of important. Now we go back to the beginning of the for each loop, which means we are now looking at another incoming edge to vertex D. We got the other two, which is A or B. I'm going to evaluate A first, okay, in this case. It doesn't really matter because it is a set, right? If it is a set, then the order does not matter. So I look at vertex A and I ask, what is the cost or what is the distance of that edge to go from A to D directly? The answer is it costs 11. And because the L value of D is 0, and then we just add the distance of this edge, which is 11. So L of D plus the distance of the edge from A to D is going to be 11. Then we compare that to the L value of A at this point, which is infinity. 11 is less than infinity is true. So we go to the then portion of the algorithm, and then we have to go do all the updates. So L of A is first updated to 11, and then we remove all the outgoing edges from A in the set E prime, but there's none at this point. So we keep whatever we have here, and then we add AD to E prime as a set. And then we also have to add vertex A to Q as a set at this point. So now we are done with everything inside the then portion of the conditional statement, and then we go back to the beginning of the for each to basically to see whether we have another incoming edge to vertex D. And the answer is yes, we have another one. The last one is coming from B. So we go through the same motion. We look at the L value of D, which is 0. And then we look at the distance of the edge from B to D, which is 3. We add those two. 3 plus 0 is 3. And then we compare 3 with the L value of B at this point, which is infinity. 3 is less than infinity is true. So we go into the then portion again, and now we update L of B to 3. And then we remove all the outgoing edges of B from the set E prime, but E prime does not have anything going out from B. So literally, basically, we don't have anything to remove. And we do have to add the new edge. So the new edge is from B to D directly, like that. And then we have to add B into the set of Q. So now it is A, B, C in Q. Now, it doesn't have to be in this order. If you list it as ACB or BAC, it doesn't really matter because it is just a set. It doesn't matter what order you use to list the content of Q. So at this point, we are done with the for each loop because we have evaluated all of the incoming edges to vertex D. Okay, because variable V is vertex D at this point. Because the for each loop is the last statement inside the while loop, now we go back to the beginning of the while loop to reevaluate, is Q empty? Q is definitely not empty. And then we go to the first statement inside the while loop, which is we select a V inside Q, and we have to pick the one that has the least L value. So we look at the L value of A is 11. We look at the L value of B, it is 3. We look at the L value of C, it is 1. So we pick C as our next V. There we go. And then we have to remember to remove C from the set of Q. And now we have to look at all the incoming edges to C. And there's only one, right? So the only incoming edge to vertex C is from vertex B. And this is where things get a little bit interesting because several people, not one, but several people asked me to check their traces, and they do not seem to evaluate the condition correctly. So let me just kind of drag the algorithm back here because this is the point that is kind of important to make, because we have to evaluate this condition. Is L of V plus D of E less than, not less than or equal to, less than L of W? All right, so now we're going to look at we are going to look at L of V. L of V, which is L of C, is 1. And then we look at the edge from B to C. The edge from B to C has a distance of 2, and we add those two together. So we got 3. In other words, if I drag the algorithm back here again, the left-hand side of the comparison has a value of 3. And then we compare that with L of W, which in our case is L of B. L of B is also 3. 3 is less than 3 is, okay, I'll let you guys tell me. Is it true or not? 3 is less than 3. It is not true. Okay, so Jack is correct, but Anita is typing 2, so I'm going to wait for her answer. It is false. Okay, so that is both correct. So Jack and Anita are both correct that 3 is not less than 3. So if I go back to the algorithm, if the condition is false, there's no else statement corresponding to this if, which means there's nothing to do. There's nothing, absolutely nothing to do in this case. We do not update L of B. We do not do any changes to Q. We do not do any changes to E prime. We are done with this for each because we have evaluated the only incoming edge to vertex C. So there's nothing to say. I mean, this row stays pretty much empty. There's nothing that we're going to do. All right. So I'm going to pause here and see if there are any questions because several people, not one, but several people made the mistake of updating L of C and then make a whole bunch of changes to E prime, in this particular step. I just want to make sure that we all understand that we don't, okay? Because, L of B is already 3, so we are not finding a shorter path from vertex B to a destination, and as a result, we don't do a single thing. All right. Alrighty. And we still got one comment coming. Or question. I cannot tell from. Alright, so maybe not. Okay. Alright, so okay, maybe yes. Alright, so this is really important. What this is telling me is not everyone in the class has taken CISP440 in the sense that they need to trace an algorithm by hand. Okay, which is what CISP440 was supposed to be. It was supposed to be taught in a pseudocode language that cannot be executed, cannot be compiled, cannot run on the computer, and people are supposed to be hand tracing algorithms. Okay, that was the original intent of CISP440. I know most people do not teach it that way, and that is unfortunate. Okay, I'm just gonna say it is unfortunate because it is really important. If they had done this, just kind of run the algorithm by hand, I think everybody in this class would have been able to trace this algorithm without, without this issue, without the issue that I'm just currently talking about. Well, it depends on who they are. I'm referring to Yolanda's text comment. Because I still teach CISP440 like once in a long while, and when I teach it, I don't use any actual programming language. I just use pseudocode to teach that class, and I make basically everybody would be hand tracing algorithms, like not exactly, but kind of like what we're doing, but in an even more tedious way. And that, I think, is the way to teach CISP440, is to really teach the concept so that people can pay attention to the ideas of a loop, the idea of a conditional statement, the idea of calling a subroutine, returning from a subroutine, and Instead, people want to teach people exactly just all the programming thing, and that missed the point entirely because I don't want the computer to run the code. I want you to run the code on a piece of paper or spreadsheet in this case. So um, I'm done ranting, so I'm good. All right, so we are now back to the beginning of the while loop. Oh, okay, I'm gonna wait for Anita's comment. Okay, so the B we wrote in the W column is the if statement. No, that is not the case, because what this is tracking is really tracking the variable W in the algorithm. The variable W is bound here. When we say, for evaluate each incoming edge to vertex V, that is when we bind variable W to be the vertex. Okay, remember in an edge, this is called the tail of an edge, because if you look at an edge like an arrow, the tail, which is where the feather is where we're coming from. So W is bound to the tail of the edge that we are evaluating, and that's why we are binding B in this case to variable W. But we definitely use it to evaluate, L of V plus D of E is less than L of W. I mean, E in this case is really a shorthand of WV, in parentheses. Okay. Yeah, so we are not really tracking it line by line because I didn't give you guys line numbers in the algorithm. But we do keep track of, the changes to the variables in this case. All right, so the next question is how the algorithm would be if changing the statement to less than or equal to. If it's less than or equal to, then we're going to do the change. We're actually going to update B again to 3, and then we're going to update E prime. We're going to remove BD from E prime, and then we're going to add BC to E prime in that case. And then we'll add B again to the set Q, but since it's already in Q, it is not going to be visible for that part. But because it's not less than or equal to, we don't do that. All right. So be very careful with these operations. I'm pretty sure in the example that I did in class, I evaluated the condition and kind of emphasized, why, the decision point, that is represented by that conditional statement. Um, so anyway, kind of important to do that. All right. This is just giving me a new idea of how I can ask questions in the final exam. Cool. Okay. So anyway, getting back to the algorithm. So now we get back to Q. Q is not empty, so out of A and B, we have to pick the one that has the least L value. B has the least value because it's 3 versus 11 of A. So this time we're going to pick vertex B as our variable V, as the value of V. So now we have B here, and then we have to remember to remove that from the set, so the set only has A left. Now we have to look at all the incoming edges to B. Let me move this out of the way. Alright, so we look at vertex B. B has only one incoming edge, which is coming from vertex A. So now we look at the L value of B. The L value of B is 3. We look at the distance of the edge from A to B. It is 1. 1 plus 3 is 4. And then we ask, is 4 less than the L value of A? The L value of A at this point is 11. 4 is less than 11 is true. Oh, I forgot to update this to A. So 4 is less than 11 is true. So now we have a bunch of updates to do. So first of all, we update L of A, and then we update E prime. So all the outgoing edges of A should be removed. So AD would be removed. and then we're going to replace it with AB. So the net effect of that is going to be, changing the AD to AB like that. We are also supposed to add vertex A to the set Q. So we can just repeat what we had already, because when you add an element to a set, where the element is already in the set, then we are not actually making any changes to Q. All right, so because AB is the only incoming edge to vertex B, we are now done with the for each loop, and then we move on to the next part of this. The next part is, I'm just looking at the graph to make sure that I'm not missing anything. I don't think I'm missing anything. So the next part is to look at Q. We at the beginning of the while loop again. We look at the set Q. We ask, is it empty? And the answer is no, it is not empty, but it has only one single element in it. So that means we're going to select vertex A, and then we remove it from the set. Vertex A does not have any incoming edges, because we can see from the graph there are no incoming edges to vertex A. So there's nothing that you need to denote from the trace, because we don't have any incoming edges. And then by the time we get back to the algorithm, get back to the while loop, the condition is going to be false, because the condition is checking whether Q is not empty, but Q is empty at this point. So then we exit the loop, and then we are done. So at the very end, we end up with E prime being CD, AB, BD. And that's the answer. That would be the solution. Do we have any questions about this trace? Alright, so the question is, for the exam, we're going to have to trace just like that. Yes. Well, you're going to have to trace it based on what the algorithm is specifying. So this is the trace when I tell you to use the document to start with, and also when the algorithm is this particular one. So in the exam, you should be careful and kind of make sure that you're tracing the correct algorithm. In fact, you should be tracing the algorithm in the exam question itself, and don't assume that that is identical to the one that you have just seen. So don't make that assumption. Yes, probability stuff is going to be in the exam, because everything that is after the second exam is going to be in the final exam. And this is also a good time to show you when we are going to be taking the final exam. This is the exam schedule, and because this class is a synchronous class, we're going to all be taking the final exam at exactly the same time. And because the start time of the class is at noon, and this is a Monday-Wednesday class, so that means this is our exam schedule. This is our final exam schedule. It's going to be on the Monday of May 17th. And then the time you have to, this is not too much of a problem because it's later than the usual start time of the lecture. So it's at 12:45 to 2:45. So we have a 2-hour final exam. It's going to be about the same as your midterm, except it's going to be a little bit longer. Shortly before 12:45 p.m., I will share a document with you, and then at 2:45 or shortly after 2:45, I'm going to collect, quote unquote, collect the exam by unsharing that document. So you might want to put it on your calendar like right now, just so that you don't forget that we have a final exam on the 17th from 12:45 p.m. to 2:45 p.m. Pacific Daylight Saving Time. So are we good there? Does anyone need more time to put this on their calendar? All right. Cool. All right. So we are good. All right. Because I really want to make sure that people, everybody remember that we have an exam, because I really hate when people miss the final exam, because they didn't write it down on the calendar. And these days, because we are not going to school, it is less likely that you're going to meet up with a classmate and you'll get reminded, oh, have you studied for the exam. You guys might be doing all of this stuff through Discord, I don't know, but some people may not be doing Discord with anyone else in the class, and I don't want anyone to forget. I just want to keep reminding people that we have that final exam. All right, so that is for this homework assignment. And we have an extra homework assignment for A star. So let me go to the A star. Oh, right there. Down a little bit. There we go. So we have an application of the A star algorithm, which is structured exactly the same way. It's exactly the same graph, except this time we have the heuristic function. And you're supposed to follow the A star algorithm instead of the Dijkstra's algorithm. So that's the only difference. No, it does count to your grade. They all add up to 20% of your grade. All of the homework assignments add up to 20% of your grade. The final exam by itself is 40% of your grade. So the homework assignments, really are not accounting for too much of your grade. Yep, that is correct. What Ivan just posted. Alrighty. So let me look at the time. We have about 40 minutes left. All right. So we got a little bit of time to get into predicate calculus. So I think I'm gonna get into predicate calculus unless there are burning questions about A star or Dijkstra's algorithm. Those two algorithms are not particularly complex, but it really is important for you guys to understand the algorithm itself. So that part is kind of important. Next Monday, we're going to have a practice final exam. It is not a final exam, it is a practice final exam. So you might want to do some studying, just to make sure that you cover all of the topics. Predicate calculus is not going to be in the final exam, so don't worry about predicate calculus or Prolog. It's not going to be the final exam, but I do want to introduce those concepts, for those of you who might be interested, and I think you should get at least some exposure of that. Sure. I mean, this assignment doesn't take that long to complete. I mean, it really should not be taking a whole lot of time because we are not going through a whole lot of iterations. So I can definitely postpone the due date. It's not an issue. But I don't think it is going to be that long. It shouldn't be it should not be taking that long to finish the assignment. So I can postpone it to the 12th, okay? And I'm not sure how that's going to help anyone in the class, but it doesn't hurt me in any way. So okay. Yeah. Okay. Well, that's fine with me. All right. Yeah, because in the final exam, if I give you something to trace, you're gonna have to do it, but like within 2 hours of time, and that's only one question, right? So in theory, you should be able to do this within maybe half an hour, 45 minutes or so at the most. Okay, because the algorithm is already fully spelled out, and we talked about it in class as well. So we are talking about the A star algorithm, which looks really hideous, but it really is not. I mean, there's a lot of shared elements between the A star algorithm and Dijkstra's algorithm. One starts with all the destination vertices, the other one starts with the only start vertex. But other than that, they do share a lot of common traits. Um, so anyway, I'm not sure what. Oh, okay. It does count to the final score. Sorry about the. Oh, so it's the category that is the issue. Okay, I see. I see what we are dealing with here. Okay, so we are dealing with the category thing. I mistakenly put it into the wrong category. So it does count to the final grade, and I just forgot to change the assignment group. It is supposed to go into just assignments and not the ones that do not count. There we go. Okay, and it's going to be the same problem with the A star algorithm. I just have to kind of change the assignment group. Thank you for letting me know. There we go. All right. So let me change the other one too, and then we're gonna go into Prolog, which is really it's really interesting because it is a different kind of AI, and I'll elaborate on what we typically understand as AI and how this is a different kind of AI. Okay, but let me do this first. Finish this one, change it to just regular assignments. Okay, there we go. Alrighty. So remember, Predicate Calculus is not going to be in the final exam, so don't worry that we don't have a chance to practice or have an assignment on Predicate Calculus. But at the same time, it is a very fun topic. Okay, so I'm gonna get into this module. Oh, okay, yeah, I should go into the homework. I'll fix that later. Um, but right now, but thank you, Robert. I definitely uh, put it in the wrong. It's still in the wrong assignment group. Should be going into homework where it's 20% of your grade. So I will fix that. So now we want to get into Prolog. Okay, so Prolog is interesting because it let you specify rules. Okay, there's a lot of reading here. I'm not gonna require you guys to read it because we're not gonna be. So on Monday we're gonna be talking about the practice final exam, and then on Wednesday, we'll talk about the solution of the A star algorithm. And potentially do a little bit more Prolog programming at that point. But I do want to show you, what Prolog looks like. Yes, Prolog will not be on the final exam. Yes, you can quote me on that one too, because it's all getting recorded. Remember. Okay, so Prolog it allows you to specify predicates. Okay, and there are different types of predicates. One type of predicate is what we call a it's basically a rule. It specifies. Okay, I'm just gonna zoom in here. Okay, because it's a little bit of this is a fun example. So this particular predicate, is a Jedi, Luke Skywalker, and then followed by a period. It's basically saying, don't ask me why, but this is true. Okay, so is a Jedi is a predicate, and then Luke Skywalker with a lowercase l is called an atom. Okay, so it is not a variable; it is a particular thing in the universe that this Prolog program is going to process. In other words, we are talking about Luke Skywalker as an individual thing in this universe makes the predicate is a Jedi true. All right. So this is not exactly a rule. It is basically a fact in the system, but it is specified in the form of a rule. Okay. We can also use this syntax here to express exactly the same thing. So this time we have is a Jedi Luke Skywalker exactly the same as before, but then we have a colon and then a dash and then true and then the period. So the way we read these rules is exactly the opposite of what you think it is. This is actually saying true implies Luke Skywalker is a Jedi. That is what it's saying. But in order for a implication to be true, especially when the left-hand side is true already, the right-hand side also has to be true. So that means, this is stating that, Luke Skywalker is indeed a Jedi. All right. So do we have any questions about this thing here? Just look at this as a fact. It is a given fact that Luke Skywalker is a Jedi. All right. So now we can specify some rules. So the rules that we're going to specify in this case is, remember, we have to read this backwards, or you can read it as is a proper Jedi, X is a proper Jedi only if X is a Jedi, and the comma can be interpreted as and X owns Y, and Y is a lightsaber. In other words, a Jedi, a so-claimed Jedi who does not own a lightsaber is not a proper Jedi. That's basically what this rule is saying. So this means we have to, in order to make Luke Skywalker a proper Jedi, now we have to define at least one lightsaber. So Anakin Blue is the name of a particular lightsaber. So this particular sentence here is stating a fact that Anakin Blue is a lightsaber. That's all it's saying. Okay, it is stating a fact. And then this one is also stating a fact of Luke Skywalker owns Anakin Blue. So we're only talking about rules here. Excuse me, we're only talking about facts, except for this one here. This is not a fact because all of everything that is in uppercase is a variable. So X is a variable, Y is a variable, and this particular rule, if you want to remember we talked about quantifiers. If a variable appears on the left-hand side, of the rule, it is a universally quantified variable. If a variable only appears on the right-hand side, like Y in this case, it is an existential variable. So the way we can read this is for all X, there exists Y such that X is a Jedi and X owns Y and Y is a lightsaber implies X is a proper Jedi. That is the way to interpret this particular Prolog syntax. We're going to skip substitution here, and then we'll get to disjunction, and we can also get to negation here. Negation is actually the interesting part. Disjunctions are basically they use semicolon to separate something into ors, but negation is the interesting part. So we'll look at this particular rule. Now this is a rule because it's not a fact. We have variables stated here. This is the negation. Backslash plus is a negation. So what is it saying? It is saying that Y is a Sith, and then the comma says conjunction, and this is negation. It is not the case that X disagrees with Y. And then we have the other side, stating this is the predicate that we want to define, which is Sith tolerant. So together, how do we interpret this? Remember, all the variables that appear on the left-hand side are universally quantified, and all the variables that only appear on the right-hand side are existentially quantified. So what this is all saying is saying for all X, there exists Y such that Y is a Sith and not X does. Okay, let me think about how to do that. X does not disagree with Y, implies X is CISP tolerant. That's what this statement is saying. And also here, that's exactly exactly saying the same thing. I just read it a little bit earlier. So now, we can go ahead and define, a whole bunch of facts and then let the system figure out, all of these things. I'm looking at the time. We still got about half an hour, so this is enough time to kind of run through a few examples. Alrighty. Oh, by the way, there's also a web resource to run SWI Prolog. So that means you don't have to install SWI Prolog. You can just run it from the web. Okay, so if you look up SWI Prolog, and we'll look up web. Let's see. There we go. Swish. So you guys can have some fun doing this too. This is one of my other examples, and just like online GDB, it would actually let you store your program online too if you sign in, as yourself. So instead of using this program, let me make another program here. Okay. All right. So Ancestor is also a lot of fun. So we'll deal with Ancestry, here, because I think the Jedi thing, the Star Wars thing, that's cultural, and not everybody is a Star Wars fan, and as a result, some of that stuff may not be understood. So we're gonna switch to something that everybody understand, which is about Ancestry. So when we specify Ancestry, we'll specify a few things. The first one is parent of. Okay, so we're going to use parent of to define some facts. Okay, who is the parent of whom? And I'm just kind of thinking, I'm going to use some fictional family in here, as an example. Do you guys have any suggestion of which fictional family I should use? Ideally speaking, we want to talk about like at least 3 generations, and with cousins defined in it. Any suggestions? I'm thinking about the Simpsons, but that is also a little bit of a cultural thing, but I can at least show you the family tree of the Simpsons. Alright, so I got the family tree. Okay, and oh, okay, Jack is typing something. Alright, so I will post this into the text channel so that you guys have a picture to refer to. My sister actually had a dog that is exactly that, a mix between a Pomeranian and a poodle. Super smart dog, also super protective as well. Yeah, kind of interesting. All right, so if you guys just refer to the picture that I posted, on the text channel, then we're going to define these relationships. So we're going to use parent of, to define a few things. So we have Abe. Okay, we're going to abbreviate Abraham to Abe. So we have Herb. Okay, and with a period, we specify this as a fact. Okay, so it's not a rule; it is a fact. So we're going to define a bunch of these facts here. Okay, parent of, Abe. Next one is Homer. And then we have parent of Mona. herb. So the gender is not a part of the ancestry thing, so we can encode gender using another set of facts. So parent of Mona, Homer. There we go. So if we want to figure out grandpa, grandma, gender specific thing, then we can define gender, right? So we can say is male. Then we can specify that Abe is a male. We can now specify female is female. Mona, like so. So you can basically see how we can use this to encode a lot of different types of information as facts. But I'm more concerned about cousins. Okay, how do we define cousins? So I'm just going to skip all the gender specification and focus on parent of in this case. So we'll now have Homer being the parent of Bart. Okay, so we're gonna do some copy and paste here. And one more, because there are 3 of them. So we have Lisa, and then we have Maggie. Alright, so when we look at the family tree, alright, so we have Jacqueline, so this is the important part. So we have Jacqueline being the parent of Marge. Oh, I should have used Marge in these parent of. I mean, not that the Homer ones are incorrect, but we also need the Marge ones because we want to define cousins in this case eventually. So we define Marge. There we go. Okay, so that's important. And then Marge has 2 sisters, twin sisters, and they're all descendants of Jacqueline. So we have Patty and Selma. There we go. And then Selma has Ling as a child. So parent of Selma. And then we have Ling. There we go. Alright. So this is not the entire family tree, but it is sufficient for us to define what is a cousin. And in fact, we can define what is a first cousin, second cousin, and so on. So this is going to be kind of fun. Alright, the first thing we need to do is to define ancestor or ancestry. Okay, so now we have to say ancestor of, and this time we are not going to use lowercase objects. We're not going to specify which element, because we want to specify a rule where we can say, we can just ask, okay, give me all the ancestor of blah blah blah. Or we can ask, is it true that X so and so is an ancestor of so and so? Okay, so we're gonna say, X is an ancestor of Y only if, okay, remember this symbol, colon and the dash is the same as only if. Okay, and we have to specify the simplest rule first, okay, which basically is just parenthood. So X is an ancestor of Y only if X is a parent of Y. So we can now specify parent of X, Y. Alright, so that defines the simplest form of ancestry. But now we're going to have to define the recursive one. So now we have to say what is an ancestor of XY. And then we now have to introduce an existential variable. The existential variable, which I'll call Z, is going to be introduced here. So we're going to say if X is an ancestor of Z and Z is the parent of Y, Okay. Then X is also an ancestor of Y. Okay, so we have to type of. There we go. All right. So this is where things get interesting because we can do it in a recursive way. Are we doing okay so far with this? Does everybody understand the recursive definition of ancestor of? Okay. All right, so with this much, I can already ask some questions. Okay, so this is where Prolog is interesting as an AI engine because it is, once it understands the facts and the rules, the first thing we can do is simply to ask who are the offsprings of March. Okay, so we can do something like this, and then we press the enter key. So this is a query. Okay, so what we are looking at here on this side is a query. It is not stating something. This is not a part of the facts or the rules that we are defining. This is a query. We're basically asking the system, can you show me all of the atoms that are children's, basically they're children of March. So we press the enter key and it says, okay, control enter to run. Alright, it complains about clauses of parent of are not together in the source file. Alright, so it wants everything to be together. Okay, fine. Because the ordering is important in the rule definition, it doesn't like to have the other facts stated interleaved with parenthood. So we just have to move things around a little bit, and I think it is not going to complain now. Okay, control enter. Alright, so it says true, but because I use an underscore, it doesn't bind it and give me the answer. So I can click next, next. It simply says true, but it doesn't give me the answer. Okay, fine. We'll go ahead and make it something here. We'll use uppercase C for child. Okay, there we go. Control enter, run it again, and this time it will tell me that if Bart is C, it will make this particular predicate true. If Lisa is C, it would also make the predicate true. And if Maggie is C, it will also make the predicate true. So this shows you, one of the kind of fun stuff you can do with Prolog is you can actually give it a question and it will give you answers. Okay, it will give you all the possible answers. Now, you can also give it something that is specific. Okay, so you can, if you say, is Ling a child of March, which is not true. Okay, so you press Control Enter, and it simply returns the answer of false because it is not the case, right? Ling is not a child of March. You can also, since now we know that March is not a parent of Ling, now we can say, but who is, right? So every time you want to specify a variable, it has to be in uppercase. So uppercase P in this particular query is a variable, and we're trying to find out, what can be this uppercase P to make parent of, in this case, P is a parent of Ling to be true. So when we press Control Enter, it will find that Selma is the only answer in this case. So it kind of works in both directions. So now the other thing we can do is Ancestor. So this is going to be even more fun because parent of is really kind of simple because it seems like we're just kind of matching these things. No rules are being used. So now we want to utilize these rules and find out who are the ancestors of a particular person. So we're going to use Maggie here, and then we are going to use uppercase A for ancestor. Now, how you want to name the variable is entirely up to you, but I just want to use A for ancestor. And then we now specify ancestor of as the name of the predicate. So when I press Control Enter in this case, it will find all the atoms that will make this true. So it will find that Homer, Marge, it will also find Mona and Abe, because all of those, because in this code it considers parent as an ancestor, which is technically true. So when I press Control Enter right now, it will say Homer is an ancestor of Maggie, Marge is an ancestor of Maggie, Abe is an ancestor of Maggie, and so is Mona. And that's, oh, Jacqueline is an ancestor of Maggie. That is true. That is true because Jacqueline is the mom of Marge. I forgot about that one. Okay, see, the program knows, and that's it. Okay, that is the last one. And it aborted the execution because it's recursively doing stuff, and it's a recursion that does not end in this case. So if I did not abort it, it would not have ended. So the reason why it doesn't end is because ancestor is the first predicate instead of the second predicate. If ancestor is the second predicate, it would have ended. Let me see, would it? Yeah, it would have ended in that case. So if I change the order of these two, then it would not need me to abort it because then it would have ended by itself. So we change this to parent of, and then we change this one to ancestor of. All right, so we'll try again, because we want to make sure that, in this case, it will automatically end. So we got Homer, yes, we got Marge, we got Abe, we got Mona, and then we got Jacqueline, and that's it, okay? So the order of, what you use inside a predicate or inside a rule is important too, because it's basically, this is called tail end recursion. Ancestor of is calling it's quote unquote calling itself. But if the first rule fails and then the second rule also fails, then it's going to go back because now it will just return a fail. In the previous case, because I have another ancestor of here, that will automatically call the recursion, which will fail the first one, but the second one would not fail, and then we'll try to find things that can match, and that's why the ordering matters in this case. Are we kind of doing okay with this? We got about 13 minutes left, and we want to define cousins. Okay. All right, so now how would you define a cousin? You can look it up. You can look up, dictionary definitions. Okay, first of all, between two cousins, they must have shared a single ancestor, right? Okay, that's good. Okay, very good, Yolanda. So we'll start with this one. Okay, we'll find out who shares an ancestor. So now we can say cousin of, okay, cousin of xy. Okay, so x is a cousin of y only if, okay, so we'll now try to specify. They don't have to be grandparents. Okay, they can be more than just grandparents. They can be great grandparents and so on. And cousins don't have to be in the same generation either. So if you look at Ancestry as a tree, we can have cousins that are of different levels of a tree, and that's when we say x number removed, right? 1 removed, 2 removed, and so on. So cousins are very generally defined in this case. Okay, but we are just going to be looking at the most general sense of a cousin. So when we use cousin of, we just want two individuals or two atoms to share an ancestor. So in this case, we can make use of ancestor of, right? So we can say, ancestor of. Now we have to introduce the existential variable, because x and y are universally quantified for every x and for every y, but the ancestor, we only need it to be existential. We just need to find a common ancestor in this case. So we're going to use uppercase A for the ancestor. So now we're saying if I can find A, which is an ancestor of x, and the same A is the ancestor of y, then we would have found, then we would confirm x and y are cousins. Okay, so we're going to try this rule and find out, okay, does it work, right? All right, so the first thing we want to try is to specify, just atoms. In other words, we know Maggie and Ling are cousins. So we just want to try that and make sure that it confirms that Ling and Maggie are indeed cousins. So we press Control Enter, and it says true. Okay, very good. Good job. And now we want to try something that is not true. Okay, so we want to find two people in this, ancestry definition where they are not cousins. So we'll go ahead and try. Oh, that's easy, right? We just use Jacqueline. Jacqueline is Marge's mom, and Abe is Homer's dad, and those two are definitely not cousins. Okay, well, at least according to the show. There we go. It says false. Okay, very good. Okay, so we now know that we can test it with specific cases like this. But if you ask it, okay, if you ask whether Bart is a cousin of Lisa, what do you think it's going to say in this case? I'm going to let you guys think about it a little bit and look at the rule that we have just set up here. X is a cousin of Y only if there's a common ancestor for X and Y. So now the question is, do you think Bart and Lisa share at least one common ancestor? Yeah, it would be true. Okay, so we'll press the Enter key, Control Enter, and it says true. You go like, no, wait, hold on a second here. They're siblings. Siblings are not considered cousins. So now, what do we have to say? To say that no, cousin. Siblings cannot be cousins. Now, there are a few things we can do. The first thing we can do is to define what is a sibling. So we can say sibling of xy, and these two must share a common parent, right? So we can say parent of, and then px, and parent of py. So that defines siblings. And now we can say, in order for x and y to be cousins, they cannot be siblings. So now we specify and then we use the negation. Remember, backslash plus, specifies negation. So now we specify negating sibling of x, y. So we're excluding, sibling, from being cousins. So with that rule change, and then we press Control Enter here, now it says false. Okay, so now we have cousin of, kind of defined. Now the fun part is to specify, what if I try to find all the cousins of Bart? Okay, what do you think it is going to find? We know it's not going to find the siblings, right? Because we just, explicitly excluded sibling as a cousin. We know it's going to find Ling because, that is proper. But it will also find something else. It's also going to find Selma. And also it's going to find, what is Selma's sister? Patty. Because they share the same ancestor of Jacqueline in this case. Aiden's typing. I'm gonna let him finish typing first before I press Control Enter to test this particular query. Yes, so grandparent can be defined that way, yes. But you can also use a numerical value to define how many levels of ancestry. So that way you're parameterizing, parenthood in terms of the level of hops. Okay, so first thing first, we'll play with cousin of first. Control Enter. It finds that Herb is Bart and Herb are cousins. And that would be true because they share Abe and Mona as ancestors. Because they're uncles, right? Because Herb is an uncle of Bart. So they are quote unquote cousins because they share an ancestor and they're not siblings of each other. Next, Homer. Well, that is funny, right? But according to the definition that we have here, Homer is a cousin of Bart because they share Abe and Mona as ancestors. Find Herb again, and then Homer again, and then it finds Marge. That is because Marge and Bart share Jacqueline as ancestors. So you can see how Patty, that's what I mentioned earlier, and Selma, that's what I mentioned earlier, and Ling, we kind of mentioned that. So this cousin of doesn't seem to be working, right? Right. So we can exclude ancestor of that will help a little bit. Okay. So let me put in the change that Aiden is suggesting. So now we can say now we have to exclude people of the same line in terms of lineage. So we can now exclude ancestor of X cannot be an ancestor of Y and vice versa, right? Because it kind of needs to go in both ways. Okay, we'll just do it with one direction first, and then test it because it will still identify certain things that is interesting because it will still identify an uncle as a cousin. So the question is, it's still identifying Homer as a cousin. That is not right because Homer is an ancestor of Bart. Oh, Bart is not an ancestor of Homer. That's why. Okay, so Aiden is right because we have to negate the opposite or the other way around too. So we have to say ancestor of X, YX. There we go. So we have to exclude the other way around too. Alright, so we're going to stop this query and then do it again. So it will still identify a uncle because an uncle is not on the same line in terms of the heritage. It will identify Patty because that's the same thing. Those are the aunties of Bart. And then Ling is what we usually think of cousin. Ling is the proper cousin in this case. So now we want to I'm looking at the time. We got a few minutes. So now you can also specify why we're getting herb twice. This particular the Prolog engine does backtracking automatically. So herb is instantiated twice because one time it is instantiated as I know why. Because according to this, we put in Abe and Mona, right? So one time, we use Abe as the A, and then the next time we use Mona as the A, and the two cases are considered separate, considered non-distinct. So that's why that's why it appeared twice because we entered both grandparents of Bart. If we had only entered one, then it would only appear once. There we go. So something that seems simple, like just defining, cousin of, is actually a little bit tricky. But you also get to see, how this is it's called an inference engine, where you can define facts. Okay, so in our particular example, all of these parent of are facts. Okay, we are just entering the givens, so to speak, into the system. We never really made use of the gender thing, which is okay, because if you want to define, grandmom or what is a mother of, then you would use the gender thing in combination of parent of. We defined ancestor of. Now, ancestor of is the first rule that we have, which basically defines, okay, how do we know that X is an ancestor of Y? We define sibling, okay, because in order for X and Y to be siblings, they must have the same parent. Um, and then we try to define something more complex like cousin of, and that turned out to be kind of like, whoa, this is kind of difficult. Um, we're almost running out of time. We got like 45 minutes left. But I do want to go back to the other tab. This one finds the shortest path. It finds the length of the shortest path as a Prolog program. The facts are stated as edges. So in this case, we got some vertices. We got vertices from 0 to v5. V0 to v5 are vertices. And then the number after that, those are the distances. Okay, so from vertex 0 to vertex 5, we have a distance of 3. So this is defining a single edge. Okay, and by using boundary and using find boundary, it can now find the shortest path or the length of the shortest path between two vertices. So that's also, it's also kind of interesting because, you kind of have to twist um, a known solution to a problem like A star or Dijkstra's algorithm. You have to think about how to re-express it using Prolog. Now, if this were in any other programming language, you cannot write A star or you cannot write Dijkstra's algorithm with this number of lines. I mean, that's just not going to happen in most cases. Okay, but in Prolog, because of the way Prolog can backtrack and basically it goes through all the combinations. When you say, this is a variable, it would go through all the combinations and see whether one works or not. So that gives Prolog the apparent simplicity. It really is not a simple programming language. It is actually a fairly complex programming language. But it allows you to do, kind of fun things like, what we just did. You can just make a query and you can ask it questions, right? So I said a little bit earlier, this is the other form of AI, because when most people think about AI these days, they're thinking about neural net stuff, right? You present a picture of something and then the computer can recognize, what it is. What we are seeing here is logic, okay? It is reasoning, it is deduction. And the Prolog engine is really just the engine itself is pretty simplistic, okay? But you can specify rules and facts in a complex way to have it to reason things out to find a solution, quote unquote solution. So I'm just going to leave it as this. And remember, next Monday is practice final exam. And then on Wednesday, if we have time, we can kind of get back to Prolog and then we can play with Prolog a little bit more. And I can also explain, why this works. Okay, how can we find the length of the shortest path, using this particular simple program in Prolog. This program does not make use of a list in Prolog, which is also a built-in type. If we had list, it would be actually easier to define the shortest path. This one does not even make use of that. This one uses what we call a successive. There's a name for that. We basically extend the boundary over and over again until we find a path from one vertex to another vertex. So this is neither A star nor Dijkstra. If you want to find a name for this particular algorithm, one name for this algorithm is C star. C as in the letter C, and then star as in A star, the asterisk symbol. So next Wednesday, if we have time, I can explain how this program works. Okay, and that's all I have for today. And then over the weekend, study a little bit so that on Monday, when I give you the practice exam, I can give you the practice exam before Monday too, so you can have some time to look at it. But the idea is, if you have any questions about that content, hopefully we'll have Monday to answer those questions. And then we also have the homework assignment due on next Wednesday. It shouldn't take you any more than 40 minutes though. Okay. Alrighty. Alright. Have a nice weekend. I'll see you guys next Monday.